Okay guys, welcome back. So in the last video I talked about a simple application of combined gas laws in which we kept the number of moles or the mass of the gas to be constant. So what happens to a gas when the mass also changes? So before explaining that, if I not watched that video on ideal gas laws, I invite you to watch that video and come back here, because that is the basis of this video. That is the equation I am using here, and I'll be solving as to what happens when what happens when the mass is changing. Alright, so I'll take a simple system to be like this. Right, and I'll take the pressure to be 3 times 10 to the power 5. 3 times 10 to the power 5 pascals. The volume to be 2 cubic decimeters. The number of moles or the mass of the gas, right? Mass of the gas to be I'll take number of moles. Number of moles to be 2 moles, right? 2 moles. And what I'm asking is, what is the value of T, or what is the temperature? What is the temperature of the system? Now, since the number of moles has been given, since number of moles is not equal to 1 and number of moles is changing, so you can put Boyle's law, you can apply Charles' law, and also since the number of moles is not a constant, you can't apply combined gas law as well. So what I'm going to do here is that what I have to do, and what is there remaining here is that the only law that I can put here is the ideal gas law. Alright. So from ideal gas law you can say that PV equals N times R times T. So if PV is equal to nRT, you have to find the value of T. So I'll isolate T first. So T equals P times V divided by N times R. Right? P times V divided by N times R. So we have to find T, so we have to substitute the values here and find T. So that's the intention of this video and the intention of this problem. Right? So the value of P, has been given. I will take this one, P, right? Not P1, V1, right? P to be 3 times 10 to the power 5, and that's Pascal. And unlike the situation in the last problem in which I put the combined gas laws, now the volume has been given in cubic decimeters. Now cubic decimeters is not the metric unit. Cubic decimeters is not the metric unit of finding the volume, right? Cubic decimeters is not the metric unit of volume. So in order to find the value of T in kelvins, what I have to do is that I have to convert into SI units, or metric units. So if V is equal to 2 cubic decimeters, you know that 1 decimeter is equal to 1 into 10 to the power minus 1 meters, so 0.1 meters. So 1 cubic decimeter is equal to 1 into 10 to the power minus 3 cubic meters, right? So 2 cubic decimeters is 2 into 10 to the power 3, 2 into 10 to the power 3 cubic meters. So unlike in the last video, I have to convert that into cubic meters because I have to get the value of T in kelvins. So I have to insert all these values in SI units. So that's the numerator. And for the denominator, the value of N has been given as 2 moles. So the SI unit is the same, 2 moles. And R I'll take as 8.3. And R I'll take it as 8.3, and joule kelvins per mole. Joule per Kelvin per mole. So this mole will cancel to this mole, and you can solve this one to be joules, right? So the pressure times volume means somewhat of some what actually happens is it is actually equal. The units are equal to energy, right? Units are equal to energy, although we don't see that PV, when PV is a constant using Boyle's law, that it is actually a type of energy or a type of work done. What actually happens is that when you are taking units, Pascal times cubic meters, will be some sort of energy, or the unit of that will be joules. So Pascal times cubic meters and joules will cancel. So only per Kelvin remains here. Per Kelvin remains, and when it go into the numerator, the unit of the whole system will be in kelvins. So the temperature of this system will be also in kelvins. So we'll solve that. So here 10 to power 5 and 10 to power minus 3 cancel, 10 to power 2, and these two cancel. So what will be remaining here is that T is equal to 3 divided by 8.3 times 10 to power 2 kelvins. Right? 3 divided by 8.3 times 10 to power 2 kelvins. So I will find the value of T. So 3 divided by 8.3. So 3 will be approximately, right? I will not solve that. So it will be approximately close to 0.4, right? 0.4 times 10 to the power 2 kelvins. So that will be close to 40 kelvins. Right? So very low temperature. Right? Very low temperature. But from this problem, I can say T is approximately 40 kelvins. Alright. So actually, you can do experiments at this temperature, but according to the values that have been given in this problem, what you get is T is equal to 40 kelvins. So that's a simple application in which the ideal gas laws also come into play, right? Ideal gas laws means when the number of moles changes, what happens to the system, and as I mentioned in one of the last videos, what happens when the number of moles changes and how we can put the ideal gas laws. So that's a simple application that I discussed in this video. So in the next video I will be discussing another application of ideal gas laws. See you then.